Hello students, in the last session we introduced ourselves to integration and also discussed about the integration as reverse process of differentiation. Today we shall study about the various methods of integration. To find an antiderivative of a given function, we search intuitively for a function whose derivative is the given function. The search for the requisite function for finding an antiderivative is known as integration by the method of inspection. We illustrate it through some examples. Write an antiderivative for each of the following using the method of inspection. First, cos 2x. For cos 2x, we look for the function whose derivative is cos 2x. Recall that d by dx of sin 2x is equal to 2 cos 2x, or cos 2x is equal to 1 upon 2 d by dx of sin 2x, that is equal to d by dx of half of sin 2x. Therefore, an antiderivative of cos 2x is 1 upon 2 sin 2x. For the antiderivative of 1 upon x, x not equal to 0, we know that d by dx of log x is equal to 1 upon x, x greater than 0, and d by dx of log of minus x is equal to 1 upon minus x into minus 1, that is equal to 1 upon x, where x is less than 0. Combining above, we get d by dx of log of modulus x is equal to 1 upon x, x not equal to 0. Therefore, integral 1 upon x dx is equal to log of mod x is one of the antiderivatives of 1 upon x. Now, let us discuss some more methods of integration. We discussed integrals of those functions which were readily obtainable from derivatives of some functions. It was based on inspection, that is, on the search of a function f whose derivative is f, which led us to the integral of f. However, this method, which depends on inspection, is not very suitable for many functions. Hence, we need to develop additional techniques or methods for finding the integrals by reducing them into standard forms. Prominent among them are methods based on integration by substitution, integration by partial fractions, and integration by parts. Firstly, we shall discuss about integration by substitution. Some functions can be integrated directly by the use of standard integrals, while there exists some functions which cannot be integrated directly, but can be reduced to the standard integrals by proper substitution, that is, by the introduction of a new variable. The method of evaluating an integral by reducing it to standard form by a substitution is called integration by substitution. The given integral f of x dx can be transformed into another form by changing the independent variable x to t by substituting x is equal to g of t. Consider I is equal to integral f of x dx, put x is equal to g of t, so that dx upon dt is equal to g dash t. We write dx is equal to g dash t dt. Thus, I is equal to integral f of x dx, that is equal to integral f of g of t into g dash t dt. This change of variable formula is one of the important tools available to us in the name of integration by substitution. It is often important to guess what will be the useful substitution. Usually, we make a substitution for a function whose derivative also occurs in the integrand, as illustrated in the following examples. Illustrate the following with respect to x. First, sin mx. For integrating sin mx, we know that derivative of mx is m. Thus, we make the substitution mx is equal to t, so that m dx is equal to dt. Therefore, integral of sin mx dx is equal to 1 upon m integral sin t dt, that is equal to minus 1 upon m cos t plus c. Therefore, integral sin mx dx is equal to minus 1 upon m cos mx plus c, where c is constant of integral. Now, for the second example, to integrate 2x sin x square plus 1, we find the derivative of x square plus 1 as 2x. Thus, we use the substitution x square plus 1 is equal to t, so that 2x dx is equal to dt. Therefore, integral of 2x sin x square plus 1 dx is equal to integral sin dt, that is equal to minus cos t plus c, which again can be written as minus cos of x square plus 1 plus c. Another example here, find the following integral, integral sin cube x into cos square x dx. We have integral of sin cube x into cos square x dx, which we can write as integral of sin square x into cos square x into sin x dx. Note here, sin cube x is split as sin square x into sin x, because sin square x can be substituted as 1 minus cos square x into cos square x into sin x dx. Here we put t is equal to cos x, so that dt is equal to minus sin x dx. Therefore, integral sin square x cos square x into sin x dx is equal to minus integral 1 minus t square into t square dt, which on simplification gives minus of integral t square minus t raised to 4 dt, that is equal to minus t cube upon 3 minus t raised to 5 upon 5 plus c, which again can be expressed as minus 1 upon 3 cos cube x plus 1 upon 5 cos raised to 5 x plus c. Now, let us look at into integration using trigonometric identities. When the integrand involves some trigonometric functions, we use some known identities to find the integral as illustrated through the following examples. Example 1, find integral of cos square x dx. To calculate the integral of cos square x dx, recall the identity cos 2x is equal to 2 cos square x minus 1, which gives cos square x is equal to 1 plus cos 2x upon 2. Therefore, integral cos square x dx is equal to 1 upon 2 integral 1 plus cos 2x into dx, that is equal to 1 upon 2 integral dx plus 1 upon 2 integral cos 2x dx. Therefore, integral cos square x dx is equal to x upon 2 plus 1 upon 4 sin 2x plus c. Another example, to integrate sin 2x into cos 3x dx. Recall the identity sin x cos y is equal to 1 upon 2 into sin x plus y plus sin x minus y. Then, integral sin 2x into cos 3x dx is equal to 1 upon 2 integral sin 5x dx minus integral sin x dx, that is equal to 1 upon 2 into minus 1 upon 5 cos 5x plus cos x plus c. Therefore, integral sin 2x cos 3x dx is equal to minus 1 upon 10 cos 5x plus 1 upon 2 cos x plus c. Now, let us discuss the second method of integration, that is integration by partial fractions. Recall that a rational function is defined as the ratio of two polynomials in the form p of x upon q of x, where p of x and q of x are polynomials in x and q of x is not equal to 0. If the degree of p of x is less than the degree of q of x, then the rational function is called proper, otherwise it is called improper. The improper rational functions can be reduced to the proper rational function by long division process. Thus, if p of x upon q of x is improper, then p of x upon q of x is equal to t of x plus p1x upon qx, where t of x is a polynomial in x and p1x upon qx is a proper rational function. As we know how to integrate polynomials, the integration of any rational function is reduced to the integration of a proper rational function. The rational functions which we shall consider here for integration purposes will be those whose denominator can be factorized into linear and quadratic factors. Assume that we want to evaluate integral p of x upon q of x dx, where p of x upon q of x is proper rational function. It is always possible to write the integrand as a sum of simple rational function by a method called partial fraction decomposition. After this, the integration can be carried out easily using the already known methods. First, factorize the denominator of the proper rational algebraic fraction into real factors which may be of the following four types. Firstly, linear non-repeated, second, linear repeated, third, quadratic non-repeated, and fourth, quadratic repeated. The following table indicates the types of simpler partial fractions that are to be associated with various kinds of rational functions. Here we have a form of rational functions and their corresponding form of partial fractions. First one, p of x plus q upon x minus a into x minus b, where a is not equal to b, can be expressed as a upon x minus a plus b upon x minus b. Second, p of x plus q upon x minus a whole square can be written as a upon x minus a plus b upon x minus a whole square. Third, p x square plus q x plus r upon x minus a into x minus b into x minus c can be written as a upon x minus a plus b upon x minus b plus c upon x minus c. Fourth, p x square plus q x plus r upon x minus a whole square into x minus b can be expressed as a upon x minus a plus b upon x minus a whole square plus c upon x minus b. Fifth, p x square plus q x plus r upon x minus a into x square plus b x plus c can be expressed as a upon x minus a plus b x plus c upon x square plus b x plus c, where x square plus b x plus c cannot be factorized further and a, b and c are real numbers. So, students, today we discussed about various methods of integration, namely substitution and integration by partial fractions. In the next session, we shall solve some interesting examples with the help of integration by partial fractions. Thank you.